Not yet. I haven't done it yet. If you hit the blue button, or press the blue button, okay. Don't hit it too hard. Okay. All right, we are recording. Let me go from current slide, which is where we're going to begin today. Bottom of page 519, but let me back up to here, and we'll do your examples here. But before we do that, let me hit just a little bit of how things are going to run. I'm going to answer all your questions now. That's what I'm doing now. I've returned the papers I could to you already, but I'll give the others when you come to turn in your finals. I'll give you the rest of them back. So we're going to cover as much, answer questions first, and cover as much as possible today, and then at the end of the day, I'll give you your last test, which will be from chapter 8. Calc 3 is. Okay, yeah, but I just thought we were way behind, so let me go and give you, okay. So chapter 8 test, and you'll only be responsible for the problems through which we covered today. So I've got more problems on there. I didn't know where to stop, so I just did what I thought was gracious plenty, and then we'll just, any you do beyond that will be bonus points. We'll talk about that later. All right, that's one thing. Two things. Number 2, have you done the student course evaluations yet?
Haven't got anything.
Okay, yeah, please do them sometime before Santa Claus comes.
To see my final grade.
You can do that if you want to, but please don't forget to do it. Okay. All right. And another thing, I may have said this before, but I'll say it again. It doesn't look like I'm going to be back on the Birmingham campus on Fridays anymore this term. The B building, the last I heard from a student yesterday, is still closed, so I don't have an office over there right now, and they'd have to find me an office, and that's just a pain in the neck. They're having to put people all over the place there anyway. And
what happened on that? I know I saw on the news there was a fire.
Yeah, there was a fire. I haven't heard for certain, but what I did hear, they think someone left a space heater on under their desk, and it either overheated or caught something else on fire. Someone said exploded. I guess that could happen, but I would think they would have those safety mechanisms in place to keep them from exploding. But something happened, and there was a fire down on the lower floor, and so whatever office that was in, I'm sure got some damage. But most of the rest of the building is just smoke and maybe some water damage. And so they're trying to repair that stuff now. And certainly my office shouldn't have been affected by anything there except the smoke and the smell. So they closed the whole building. And they may be still investigating what caused the fire. In case it wasn't a more problematic electrical problem, they may have to do some rewiring. But if it's something like that, that was a human error. But if it's something intrinsic to the building that was wrong, they've got to do some more stuff to it. So last I heard, they still have it closed. So I'll be here Friday from 8 to 12. So if you need to come in, don't go to Birmingham campus, come here. All right. And there were questions. And you said page 481, section 7.4 exercises. You said number 9, was it? Okay. So let me get all that written down. I want to make sure I had it right in my head. Okay, so this is page 481, 7.4 exercise, and number 9. Okay, now what it says here, find the arc length. Okay, in these exercises, find the arc length of the graph of the function over the indicated interval. So this is 9 is y is equal to 2/3 x to the 3/2 plus 1. 2/3 x to the 3/2 plus 1. Okay? And we're integrating that from 0 to 1. Okay. I returned 1 or 2 papers to you there on your desk. Now, you needed the third test, is that right?
Yes.
I think I gave you test 1 and 2, didn't I?
Yes, sir.
Okay, so third test is somewhere in here. one of you guys, does it start with find the area of a region bounded by?
Yes, sir.
Okay. This is it. This says test 1, but it's really test 3.
Yes,
Yeah,
sir.
okay.
Thank you, sir.
I want to make sure I didn't give you the key, right? Okay, good. I knew you wouldn't want that. Okay. All right. So this is our problem. That's the one you're looking at, right?
Yes, sir.
Okay. And it says find the arc length. Okay. Now remind me how we do the arc length. They usually call that S is equal to,
And then it's the square root of 1 plus f prime squared.
dx, right? And this is going from A to B, right? All right. So what's one of the first things we got to do?
Find f prime.
Yes, find f prime. Take a derivative. In this case, it's what we're calling y prime. So let's do y prime is equal to, and here's Daniel. And for some reason, I'm putting you in the wrong place. Okay, let me put you in the right place. I'm going to put you in your place. Okay. All right, there's Daniel's. Good deal. So what is y prime?
X to the 1/2.
X to the 1/2. Perfect. And then what's the next thing we're going to do?
Would be square that.
Square it. Okay. So y prime squared is what?
Just x.
X. Very good. This is working out nicely, isn't it? So what we have here, the arc length is the integral from
The square root.
from
0
to 1. That's all, the limits on x of the square root of
1 plus x.
1 plus x dx. That's it. Okay. Now, I don't like trying to take integrals of radicals. So how is another way I could write this? Integral from 0 to 1 of,
Say 1 plus x to the 1/2.
perfect, okay, times dx, okay? Now at this point there's a couple ways you could go. How would you like to go? And don't mean away from here, okay?
We would take a antiderivative.
Okay. Gonna work with this one, is what I assume that means. So the antiderivative of 1 plus x to the 1/2 would be
X.
okay, you could say x plus 1, is that what you're going to say? 1 plus x, x plus 1, it doesn't matter.
Well, it'd be 1x. If we came at the way ahead, it'd be 1x.
Okay, how'd you get that?
Because aren't we going to use the chain rule and take the derivative of the inside and multiply it by. We're doing antiderivative.
Yeah, we're doing antiderivative. Okay. You're trying to confuse me, weren't you?
I'm trying to confuse myself.
Okay. So I'm going to erase what I wrote because you were telling me something else. Okay. Okay. What would the antiderivative of 1 plus x to the 1/2 be? Now, if this is the way you want to do it, we can do it another way.
Well, I'm confused, so
Okay.
let's try the other one.
I don't know if if you're comfortable enough with your integrals yet that you, well, let me put it this way. If you'd rather do a substitution, if that's easier for you to see, or just working with this, what you think? Huh? Substitution. Okay. What do you think you would substitute? Yes, let u equal 1 plus x. This is going to be a very simple substitution. Then, what's the next step in substitution? du is equal to? Second?
X.
Nope. Take a derivative of that. Derivative of 1 is 0. Derivative of x is
1
dx. 1 dx. Right? All right. That's what I said. This is going to work out really nicely, I think. Okay. So let's write down our integral, but we're going to be changing to u. See, the du is going to be dx, so that's just going to become a du. And this thing right here is your u to the 1/2, right? So it's u to the 1/2 du. Isn't that what you got? 1 plus x is your u to the 1/2, so it's integral u to the 1/2, and then your dx is du. So you write du. What we haven't done is what? What's the glaring skip over that we've done? Our limits. So that is, this is whatever your variable here following the d is x. X equals 0, what would you equal?
1.
1. Okay. And when x is equal to 1, what would you equal? Second? Okay. 2, exactly. All right. Now let's evaluate. What's the antiderivative of u to the 1/2?
1/2 u to the negative 1/2.
Okay. I'm sorry. I meant to say antiderivative.
Oh.
Oh, okay. My bad. Okay.
So that would be u to the 3/2 over so it'd be 2/3.
2/3 u to the 3/2. Perfect. That's what we evaluate from 1 to 2. Okay. Now this is where it comes out a little squirrely, but okay. I'm going to factor out my 2/3 so I don't have to carry that around anymore, okay? Okay. Now, we're going to have to take, for the upper limit there, plug in 2 for u. Okay? 2 for u and u for u. Never mind. That was an old song. Okay? 2 to the 3/2. Well, you can't take the square root of 2. That's the square root of 2. But you could cube it, and that would be 8, and then take the square root of 8, which I hope all of you remember is 2 root 2. You buy that? Okay. So it's 2 root 2. That's the upper limit. Okay. Minus, now let's plug in the 1. That's a lot easier. What's that? 1. Okay, good. All right, there's your answer. Okay. If you actually want a numerical value, pull out your calculator, do 2/3 times parentheses 2 root 2 minus 1, close parentheses, equals you got an answer. I don't know, recall, do you know what answer they gave in the back of the book? Okay. Let me see which way they did it. I'll get you marked here in a minute. If I can remember where the answers are back here. This is chapter 7, wasn't it? 4. .2, 7.1. 7.1, 7.2, 7.4, number 9. No, that's 19. Okay. 2/3 of the 2 root 2 minus 1, and then they give an approximate answer. So, yeah, that's exactly what they got in the back. Okay? Does that answer what you needed?
Yes, sir.
Okay. Good deal. Let me mark Vince here. And Vince, if right after class, if you'll come up, I'll give you your test 1 back. Everybody had finished it, but not everyone has finished test 2. So I don't know. Has everyone finished test 1? Did you turn in test 1? Okay, get it back to me. Get it? I need it. Huh?
I got tested.
You got test 2, yeah. Finished and turned in?
Yeah.
Okay.
Well, no, not finished. I mean, not turned in, but finished.
Okay, good. Okay. All right, well,
I can give that to you later.
okay. That's when you come to turn in your final at the end, I'll give you your test back. Okay, sorry. It doesn't depend on that, but. All right. Were there any other questions? This was a review from chapter 7. Any others? Before we get started on where we left off in chapter 8. Okay? That it? That's the only one you had? Okay. Then let me clear the screen here. Well, no, I can just go to the next page. All right. We're in chapter 8, 8.1, and the procedures for fitting integrands to basic integration rules. Okay? These are just some, you might call these tricks, okay? You might call them methods or procedures, okay? If you started with something like this, that might be a little bit more difficult to do, sort of like we did this time, the example we just did, except that was a square root. You can't really expand the square root, but if it's a square, go on and multiply this through. Because to take an integral of this, might be able to do it, but it may be easier to go and square this. That'd be 1. 1 times 1 is 1. Twice 1 times e to the x, 2e to the x, and then square e to the x is e to the 2x. And here's Catherine. Okay. Wow, team. Almost perfect attendance if we can get one more to show up. Okay. So this is something quite, I think you see that would be pretty easy to integrate. You have a little bit of work to do, but a little bit less confusing maybe than that. Okay? Maybe not. Whatever. Okay, another thing to do, if you have this kind of situation, that is not a particularly easy thing to do because your most complicated part is your denominator. Derivative of that is not your numerator. Okay? So therefore you can't do a direct substitution. But what you can do is split this into 1 over this plus x over that. Okay? Now this will be something like a trig substitution. Okay? And this will, well, a trig identity, that type of thing, inverse trig. And this will be that you can do a substitution on. Okay? So there's another trig. Okay, this one. Okay? They say complete the square. I'm not sure I ever would have thought of completing the square down here. And when you do complete the square, it produces really strange things. So that, I don't think I've ever done it in that context. I've completed the square before, but I'm not sure I would have ever thought of doing that here. And in fact, I don't even see exactly how they got that. Okay, I think I do know, but that is nowhere close to the type of thing I would look at and say, oh, let's complete the square. Okay. Now, here's another one. If you ever have a rational expression that's what we call improper, Proper would be the degree of the numerator is less than the degree of the denominator, like this one. Okay, that's proper. This one, the degree of the numerator and the denominator are the same, or if the degree of the numerator is greater, that's what we call improper. Well, if you have that, then divide first and then integrate. You can integrate this almost with your eyes closed, but don't. Okay, and you can integrate this using a trig and inverse trig thing. Okay, so yeah, you can always. That's usually your first step. If that rational expression is improper, divide first. Okay. Now, this is definitely a trick. Okay. Definitely a trick. If you look at this, sure, the numerator is the derivative of the first term here, but not the second term. Okay? You would need a +2 in it. Well, since you need a +2, why don't you add a +2 to it? But then you have to subtract the +2. Well, then this part, now you split it like you did up here. This part is a easily substitutable. Okay? Just do let u equal the denominator of that, derivative of that is your numerator, that's fine. Then when you get to this part, that's 2 over, do a substitution here, and make this u 2 over u squared. That's 2 times u to the -2, and that's just a power rule. Okay? So that's, yeah.
How do they get the x plus 1 on the right?
Okay. This is a perfect square. Right? X plus 1 squared. So that's what they did. They wrote this one out, but wrote that one as perfect square. Okay? Use it trig identities. Cotangent squared is equal to cosecant squared minus 1. Yeah, I like to use that one all the time. Okay? Multiply and divide by the Pythagorean conjugate. Okay? In other words, multiply by any kind of a conjugate that works. You know, but this is Pythagorean. If you multiply by 1 minus sine x, this becomes 1 minus sine x squared, which is cosine squared x, and then you can simplify things with that. Those are just tricks to do. Okay? Try what works. Okay? Try to get it into a form that you think will work and go for it. Okay. And that finishes 8.1. I think I assigned all these before, but if I didn't, let me assign them now. Do number 3. It's at calcchat.com. Do any of the odds 5 through 13. They're all at calcchat.com. 7's at calcview.com. Do any of the odds 15 to 45. A whole passel of them there. They're all at calcchat. 17's at calcview. 47, it should be at calcchat. 49 should be at calcchat. 51 through 55, any of those odds, they're all at calcchat. Any of the odds 57 to 71, they're all at calcchat. 59's also, at calcview. Do either 73 or 75, they're both at calcchat. 77 or 79, they're both at calcchat. 81, you can think about doing that if you want to. That should be at calcchat. Then you can try 83 if you'd like, or 85. 87 should be at calcchat. 89 should be at calcchat. And then any of the odds, well, 91's a volume problem, that's a calcchat. 93's an arc length problem, that's at calcchat. And number 95 is a surface area problem, that should be at calcchat. Average value of a function, that's number 97. That should be at calcchat. Arc length, 99 should be at calcchat. Finding a pattern, you can do that if you want to, and or methods of integration. Okay? Which, if you have computer algebra system, I guess it's a piece of cake, but if you don't sweat it. Okay, and that's it for 8.1. Let's get as far as we can in 8.2. Why did I do that? There we go. Discard and go to 8.2. All right, we're finally getting into a technique. That was the title of it. Earlier was just showing us tricks, you might say, or things you might try, which I guess are counted as techniques. Here we get into what we really consider the techniques. Again, Chapter 8 is integration techniques and improper integrals. We're not going to get the improper integrals. The first technique we'll be doing, besides those we just looked at, will be integration by parts. We'll find the antiderivative using integration by parts. Okay? Now, what integration by parts is, in this section you'll study an important integration technique called integration by parts. This technique can be applied to a wide variety of functions, is particularly useful for integrands involving products of algebraic and transcendental functions. For instance, integration by parts works well with integrals such as this. Okay? Here's an algebraic function, there's a transcendental function. Product of those, this will work. We'll see that later. Algebraic function, transcendental function. That will work. Transcendental function, trig function. That will also work. Okay? And in fact, let me give you the rule now. I'm sure they're going to give it to you later. Here's what you look for. You look for a product, obviously a product. One of those features in the product, one of those multipliers in the product, what you want to do is pick one that simplifies when you take okay, this sounds crazy, but it's what we're going to be doing. It simplifies when you take a derivative, and most of them will do that, but it doesn't get, but the other one can't get any more complicated when you do an antiderivative. Because remember, antiderivatives usually go up in powers, so they would get more complicated, whereas derivatives usually reduce in power. Okay? So, if you look at this one, this is a strange one. This one, if you take a derivative, okay, you actually get that. No, you don't get that, but you get something related to it. So, this will get simpler. And when you take the antiderivative, it does get a little more complicated, but not too bad. Okay? So we'll come back to that. This one, you take a derivative, this gets simpler. Antiderivative, that doesn't even change. So that's a good candidate for integration by parts. This one, you take a derivative, antiderivative doesn't get any worse, it stays the same. This one, you take a derivative, and it stays about the same complexity. You might have to do it again to get it back to sign, plus or minus SIG inside, but that will work too. So that's what we're looking for. Products that if you take a derivative of one, it gets simpler. The antiderivative of the other, it doesn't get much worse. That sounds really strange here, but that's what we're going to look for. So it all goes back to the good old product rule for taking the derivative. Okay? You take a derivative of uv, what is that derivative of uv? Go back to Cal 1. What's the derivative of u times v?
U plus v.
Say again?
U plus v.
I don't think that's the sum of uv. That's not the derivative of
So
uv.
it's going to be u over v?
That's the division of functions. What is the product rule for taking a derivative?
The derivative of the first times plus the second, plus the derivative of the second. Whatever, if I was writing it down, I'd say it right.
Okay. It's the first times derivative of the second plus the second times derivative of the first, right?
I should have been more specific.
What's that?
I said I should have been more specific.
Yeah. Well, you said it correctly. Okay. So that's what we got. Now, here's where the key comes in. If you have in your integral a function and the derivative of another function, either or, it doesn't matter. If you can get that, then you can go back and say, well, that's the same as the integral of this minus the other one. Okay? Well, the integral of this is just going to be u times v, because the integral of the derivative, the perfect derivative, is going to be just that. And then you change from this one to that one. See, in other words, you take the derivative of one and integrate the other. So that's why I said if you got something that the derivative gets simpler and the antiderivative doesn't get any worse, then integration by parts works. Okay? For both u and v are differentiable functions, of course. If they weren't, you can't even do the product rule. So when u prime and v prime are both continuous, you can integrate both sides of the equation, and this would just be uv, and that would then be that integral. This is a weird way to do it, but it's okay. And by rewriting this equation, and here's what they did, u v prime dx, this is sort of weird they did it this way, plus v u prime dx. Well, v prime dx is dv, and u prime dx is du. If you think of u as a function of v, it's v of x, and v is a function of x, then v prime dv would be derivative of v times the derivative of x. So that's exactly the same. Okay. So by rewriting this equation, if this is one you started with, integral of u dv, and you don't know what to do with it, then write uv, the product of those two, minus this one. If that gets simpler, then you've got it done. Okay? So that's the key. This is blah, blah, blah. When you actually do them, I think you see it gets a little easier. We hope so. The formula expresses the original integral in terms of another integral. So depending on your choices of u and dv, it may be easier to find the second integral than the original one. That's what we're hoping for. Because the choices of u and dv are critical in the integration part process, these guidelines are provided. They like giving guidelines, don't they? Okay, try letting dv be the most complicated portion of the integrand that fits the basic integration rule. Then u will be the remaining factor of the integrand. Or try letting u be the portion of the integrand whose derivative is a function simpler than u, that's what I was saying, then dv will be the remaining factor. Note that dv always includes the dx in the original integration. So, again, a lot of blah, blah, blah. Let's see how it works. Well, not yet. Okay. When using the integration by parts, note that you can first choose dv or first choose u. Yeah, either one, doesn't matter. After you choose, however, the choice of the other factor is determined. It must be the remaining portion of the integrand. Also note that the dv must contain the dx. Okay? So we'll get these rules down. Okay? This will start off feeling a little bit like a substitution, but it's not the same. So here's one. Okay? Now again, here's what we're trying to do. We're trying to pick the u so that when you take a derivative, it gets easier, and the v so when you antiderivative, it doesn't get any worse. So in that case, let me get my pen set up. In that case, what do you think your u is going to be? Let u equal, guess what?
E to the x.
No, that's the part we want to antiderivative. So that's going to be our dv. It'll be e to the x dx. Always the d one here has to have the dx in it. Right? So u is going to be x. Okay, got it. Now, then, okay, what we're going to do is take derivative of u, and what would that be? du is equal to 1. What next? It's actually taking a differential dx, okay. Then du will be dx. That's the part that looks like the substitution, right? That whole left-hand side. Over here, we're going to integrate this. Antiderivative, okay? And what's the, in fact, you can do your little integral sign if you want to. What is the antiderivative of dv?
E to the x.
No, okay, yeah, but that would just be v, right? Okay? And then this will be e to the x. Absolutely correct. Okay? You see that? When you took derivative of the first part, it got easier. When you integrate the second part, it didn't get any worse. Right? Okay. So that's how you choose the thing. Okay? That's the setup. Now here's how you solve it. Okay? Remember, this was u times v, so you just multiply these together. So this thing here is equal to u times v, which is x e to the x. Done. Minus the other integral, which is your bottom line here. And that bottom line is the integral of v, which is e to the x, du, which is dx. And I can do that, right? I couldn't do the first one very easily, but by integrating by parts, picking one part to be the u, the other the dv. The u, when I take a derivative, we hope to get easier. It did. When I do the antiderivative of the integrate the dv, hopefully it gets no worse. It didn't. So then we go back to the u times v minus the integral of the reverse, v du, the bottom line here. Okay. So this will be x e to the x. And what's the antiderivative of e to the x? E to the x. And then, of course, we need a plus c, because it's indefinite interval. Plus c. There's your answer. That one, I can't do looking at it. No, it's a product. There's nothing I can do with it. So I use integration by parts, or I try it anyway. Let one part be a u and the other be a dv. Then I do a du, figure out what v is. The u times v, that's going to be the first part, minus the integral of v du. V du, the second part. And that was a pretty easy integral to do. But, of course, I have to put a plus c at the end. All right. That's how we did it. Let's see how they do it. Y'all want to leave that a little bit longer, or you need it? Got it? Everybody got it? Okay. Let me erase the ink, and let's see what they do. To apply integration by parts, you need to write the integral in the form of the integral of u dv. Okay? You don't have to write it that way. If you just start doing, let's take that as a u and dv. Okay? There are several ways to do this. That could be x be the u and dv be the e to the x dx. That's what we're going to wind up doing. You could do e to the x is the u and x dx is the dv. You could do 1 is a u and x. That doesn't help you at all because you're just integrating the same thing. You can let that be your u and that be your dv, and that really doesn't change much either. Okay. The problem with this, you take a derivative of this, it doesn't get any worse. Okay? Integrate that, it does get worse. That would be x squared over 2. Now it's more complicated. Okay? This one winds up with the same integral we had to begin with, so that doesn't help us any. And this, I can't, the derivative of this has 2 pieces to it, and so that actually gets, to take the derivative of that, it gets more complicated. This is the one, when you take the derivative of this, it gets simpler. Integrate that, it doesn't get any worse. That's the one we choose. Okay? The guidelines for integration by parts in the earlier slide suggested the first option because the derivative of u equal x is simpler than x. It's just dx. And the dv equal e to the x dx, the most complicated portion of the integrand that fits the basic integration formula, and that would then be, okay, let's see, yeah, okay, this is your dv, e to the x dx. If you integrate both sides of that, that would be integral of dv is v, that's what we're saying here, and the integral of this thing is e to the x. So that's what you said. Okay, so your x Your u is going to be the x, du is dx. Take the derivative of that, just like you did with substitution. And up here we have the dv is e to the x dx, and we find out v is e to the x. Now the integration by part produces, this is the original thing, the integral of u dv is equal to uv minus the integral of v du. Okay? That's where I just go to u times v, that's this part, minus the, I'll write it on the bottom line, but v du. Here's v du. The integral is e to the x dx. Okay? That's the v du, and that's what we integrate, and that's a pretty simple integration. So your original problem, that's what you had to begin with, is equal to uv, which is x e to the x, minus the integral of e to the x dx, which is exactly what we did, and that gives you x e to the x minus e to the x, and then you have your constant, plus c, because it's an indefinite integral. To check this, differentiate that, see that you go back to the original integral. If you want to check it, by all means check it. Okay? As you gain experience in using integration by parts, your skill in determining u and v will increase. The next summary lists several common integrals with suggestions for the choices of u and dv. So let's make sure we did example 1. If I'm reading this right, they're skipping example 2, example 3, example 4, example 5, and example 6, okay? Thank you very much for all that help here, okay? So let's go back and us do those. All right, we will do them here. Example 2. Integrate this. X squared log x dx. Okay. Now, this is almost an exception to the rule. And here's why it has to be an exception to the rule. Normally, you look at this and say, if I take a derivative of that, it gets simple. But that means you have to integrate that. Does anyone know what the integral of log x is? No? Okay. Well, I know what the derivative of log x is, so that's going to be all right. That means I have to integrate this, which is going to get more complicated. But we can live with it. Okay? So, let's let here, what is your first choice is, what is going to be your u? Second?
Log x.
Log x? Okay. Then dv has to be the rest of it. And what's that? X squared dx. Perfect. Don't forget the dx. Then what do we do next? Du is equal to, and what is du?
X.
What's the derivative of log? Anybody? 1 over x dx. Okay, always put your d with the d's, okay? Then, integrate this. That gets a little worse. V is equal to? X cubed over 3. Perfect. Okay. Don't mess with the plus c's at this point. We'll get those at the end. Okay? Now, here's what I say. Start with the uv. Multiply them together. So the answer, this thing that we started with, the first part of the answer is x cubed log x over 3, or 1/3 x cubed log x, however you want to write that. It's the product of those two, minus the integral of the bottom line. That's how I do it. That's why I write them this way, okay? So I always do that at the bottom, okay? Well, that integral is going to be, I'm going to put the 1/3 out front, and here we have an x cubed, there we have a 1 over x. What does that yield? X cubed over x is x squared dx, right? You got all the pieces in there. Okay? Even though that got, a little bit more complicated, I can still integrate it by itself with no logs in there. So I'm a happy camper. Okay? So this gives you x cubed log x over 3, or 1/3 x cubed, okay, minus, and then what's the antiderivative of x squared? As if we hadn't done that before. X cubed over 3, okay? And then you have your plus c. Don't forget your plus c with indefinite integrals. So this is, you can write it any way you want to. I'm going to write it this way. 1/3 x cubed log x minus 1/9 x cubed plus c. Now, if you decided that you wanted to factor out the things that were common, you could say this is a 1/9 x cubed times 3 log x minus 1 plus c. And if that tickled your fancy, you could do 1/9 x cubed times log of x cubed minus 1, which is just sort of clever in that you got everything in terms of x cubed, because the rule of logarithms, constant times the log is the log times that argument raised to that. It's just a rule for logarithms. Any one of those three answers are fine, and you could probably do other variations of them. Factor out a 1/3. There's all sorts of things you can do. Let's see how they left it. This was example 2.
Your open window is becoming a problem.
Oh, okay.
Did you put it in this? Not really.
Yeah. Yeah, and they love to come right under my window. Okay. So actually the answer they give in the book is pretty close to this one. I started so that one there. What they put x cubed over 3, which is the same, log x minus x cubed over 9 plus c. So there's lots of ways you can write the answers. Actually, any one of those 4 plus the way they did it, you can just mix and match any way you want to, as long as you do it right. Okay? Now, the key here, and this is one reason I don't use WebAssign. If I had given this in WebAssign, they would look for one of those answers and only one, and you might spend the rest of the day trying to figure out either what you did wrong when you did nothing wrong, or, well, which answer are they looking for? And there's just so many different ways you can compose those answers. Like I said, you can leave it like this. They pulled out the x cubed over 3 times log x and made this x cubed over 9, or you can do 1/9 x cubed. There's just so many possibilities there, it will drive you crazy. Okay? Yeah.
The last one doesn't require a plus C.
Again?
I was seeing the last variation doesn't require a plus C.
Yes, it does. Yes. I'm sorry. I just hadn't written it down. Yeah. Right. All of them require a plus C. Absolutely. There are other possibilities, but I won't even go into those. Okay. Now they say you can check your result, whatever result you got, by taking the derivative of it and seeing if you wind up with that integral. You should. I usually don't take the time to do that, especially when we're running so short a time like we are now. Okay. Let's go to example 3. Here's example 3. Evaluate that. They checked something else in on us they hadn't told us about yet, but we'll do it. I'll show you how to do it. The integral, this is a definite integral from 0 to 1 of inverse sine of x dx. Okay. Now I'm trying to remember if we even have that. I don't recall that that's in any table. It may be. If it is, I'd look that one up in a table. That's all I would do with it. But if you can't find that in the table, which I'm guessing you probably can't, okay, here's what I would suggest doing. This is first shot. Let that be my u, and that be my dv. Because I know we can look up in a table and find the derivative of an inverse sine. Okay? And then that being a dv, when you integrate that, it's going to get a little more complicated, but I don't even know how to do an antiderivative for that, because I don't have any formulas in my mind that would work on that. So that's what I would suggest doing. Let's see what they, yes, that's what they do too. Okay? So here they say let u equal inverse sine of x and dv equal dx. Right? Then you get your du, and this one I almost have to go and look up in a table, but I think I do know what it is. I'm pretty sure that's 1 over the square root of 1 minus x squared. Isn't it? I think my table of integrals is back.
It's on the first page of chapter 8.
What's that?
It's on the first page of chapter 8.
Yeah, it probably is there. Okay. Let's see. Yes, you're right. Well, wait.
I don't see the inverse.
Okay. Those are integrals, not derivatives. Okay. I think your table of derivatives and integrals are in the back of the book, and the integration tables are table B. Do they have the derivative tables? I don't think they do. Yuck! You rotten things. Okay. Here it is. Very front part of your book. Basic differentiation rules. The derivative of arc sine. Number 19. Front inside cover of your book. Very front inside cover of your book. Derivative of arc sine of u, but u is x here, is u prime over 1 minus u squared. Well, u prime is your dx, so that would be dx over that. And the antiderivative of of dx would be, it's easy, x. Got it. Okay? So what your answer is, the product of u times v, which is equal to x times the inverse sine of x. I like inverse sine better than arc sine, but if you like arc sine, use that, okay? Minus the integral of the bottom line, okay? And the integral of your bottom line here is x dx over the square root of 1 minus x squared, right? Now, that doesn't look a whole lot better, or does it? What might you do to that second integral? Anybody? Second?
I was gonna say substitution.
Substitution, yeah. And what would you substitute? Now, if these same letters get you confused, use different letters. But if you're okay with them, we're just used to use. Let u equal what?
1 minus x squared.
Perfect. Then du?
3x.
Second?
3x.
Okay, it's certainly got a dx in it, but there's got to be more than that.
3x.
Where'd you get?
No, 2x.
Okay, I agree there's a 2x in it, but that's not quite it. Minus 2x, right? Derivative of 1 is 0, and derivative of minus x squared is minus 2x dx, right? Okay. Now, that's not quite what you have up there. We only have an x dx. So let's divide both sides by minus 2. Divide both sides by minus 2. Okay, so that will then produce, that minus here will then become okay, let me write it all down. X times the inverse sine of x, and the minuses, minus a minus is plus 1/2, because that's 1 over 2, the integral of du, because we've got the minus 1/2 out front, okay? But I'm also going to, I'll do it, over u to the 1/2. I'm going to do that part anyway. Your u was 1 minus x squared, and the radical means the 1/2. Now, I don't like integrating there, so I'm going to bring this down one more step. Inverse sine of x plus 1/2. And I'm going to write that integral is u to the minus 1/2 du. Is that all legal? Above board. Not too much shell game there going on. Agreed or not? Okay. Now, what's the antiderivative of u to the minus 1/2? Antiderivative of u to the minus 1/2.
2u.
Second?
I'm thinking it's 2u.
2u, happy birthday to you. No. 2u to what?
No, that'd be
Negative 3 over 2.
No, 1 over 2.
it's supposed to be
You increase the exponent by 1. Right? So that makes it a 1/2. And then you divide by 1/2 is the same as multiply by 2. So that's where the 2 comes from.
and not be able to. Or
This 2, or are you throwing another 2 around there?
oh,
If you divide by 1/2, it's the same as multiply by 2.
okay. I see.
Yes, sir. What's that? Sure. That's not quick enough. Okay. Good deal. Thank you. You didn't have to wait for Monday. Good.
I forgot that we weren't doing anything in other class.
That what?
We weren't doing anything in my other class, so I just finished that up.
Well, I want to know what class that is. I'm never going to get out of here. Okay. All right. Does everybody agree with that now? When you integrate, this is a power rule, okay? You increase that by 1. That makes it a positive 1/2. Divide by your exponent, which is divided by 1/2, which is simply multiplied by 2. Okay? So that's it. That's all there is. Now this 1/2 and that 1/2, yeah, they cancel out. And that 2, I'm sorry, cancel out. Now we should put a plus c in there, but I'm going to wait just a minute and do that. Okay? So this will be x sine, inverse sine of x. Now what's wrong with this picture the way it is now? You have x's out here and u's there. Not good. But we know what u is, or u are, right? Yeah. So let's go back and plug that in. So that's going to be plus 1 minus x squared to the 1/2. Now I put my plus c. You could have put it earlier, but I just waited till the end so I wouldn't have to write it so many times. Now, if you don't like having exponents here, since the original problem, no, the original problem didn't have that, that's perfectly fine, okay? Let's see how they left theirs. X times the arcsine, they like to say arcsine of x, plus 1, they wrote it as square root of 1 minus x squared plus c. So I wrote it as to the 1/2 power, they did that. So they did go back and do that. X, they wrote arcsine, I'm writing inverse sine x, plus the square root of 1 minus x squared plus c. Okay. Rather than write it in exponential form, they wrote it in radical form. Yep, that's it. Now, if you're integrating something you don't know the integral for, but you do know the derivative for it, let that be your x, and then the dv is going to be the dx part. So that's sort of the little rule there. Oh, I'm sorry. Yuck. I messed that up. Because this wasn't an indefinite integral, this was a definite integral. So I should have carried around my limits here, 0 to 1, okay? But when I changed to the u's here, I needed to take care of that. And what would that be? The x is going from 0 to 1. So when x is 0, u is 1. And when x is 1, u is, that second? Really? 1 minus 1 squared. That's a 0. Okay. That then turns this around. Sorry about this, folks. I'm going to erase everything below that, or some of the stuff below that, because I don't want to erase everything, okay? Because I was thinking it was still indefinite integral. I forgot completely it was a definite integral, okay? I'm also going to have to explain this to you, because I didn't earlier. This part also needs to be evaluated between 0 and 1, even though it's not an integral. So this has to be evaluated from 0 to 1, okay? Now when I do this one, I don't like having the larger limit on top, on bottom, and the smaller on top. So to take care of that, I change it to 1 minus 1/2 the integral of 0 to 1 of du, u to the 1/2 dx. Yeah, u to the minus 1/2 du. That's what we did before. But because of those limits, I had to change the sign again back to a negative. So that thing is going back and forth like a ping pong battle. Okay. So I think I will erase all this at the bottom, okay? Now, because you do evaluate even that first part, even though there's not an integral involved, but there was originally, you have to do it. If I plug in a 1 there, what does I get? What does I get? That line right there. If I plug in a 1, what does that give me?
1 inverse sine of 1.
Okay. I'll do the second part. Minus 0. Okay. Did I do it right?
I think so.
Okay. Because plug in a 0, you get nothing. Minus 1/2. And what was that integral again? You remember it?
Du over u to the 1/2.
U to the 1/2 divided by 1/2, which is multiplied by 2, And this is evaluated from 0 to 1. So those go away. So what do we have here? What's the inverse sine of 1? I don't know if y'all remember how we used to do this. You may not have been in my class. Here's what I do. I think of it this way. I want to write this in another form. But I'll go back to my trig function. A trig function of an angle is equal to some number, right? So an inverse trig function, you operate on a number and it gives you an angle, right? That's the inverse part of it. Does that make sense? So basically this is implying there's some angle here, theta, that when I take the sine of theta, I should get a 1. This one here. That one is just a coefficient, okay? And what angle, if I take sine of some angle theta, does it give me 1?
Pi halves.
Pi halves, you got it. So this over here is just the angle pi halves minus, and then we evaluate this from 0 to 1, okay? Well, 1 to the 1/2 is, in other words, the square root of 1 is 1, minus the square root of 0 is 0, okay? So basically we have pi halves minus 1. I forgot that it was a definite integral. I left them off, and therefore they were missing. So the answer is pi halves minus 1. And if you remember what pi halves is, pi is 3.1416, so pi halves would be 1.57 blah blah, 08 or something like that. And then subtract 1 from it, you get 0.57108 or something like that. Okay. So sure enough, they got the right answer. I forgot they had limits on it. Yes.
Using substitution a second time, could we have done factoring like Prof suggested?
Okay, so there's one more time.
Instead of using a second substitution, could we have done factoring? Prof suggested that earlier.
Where?
The second substitution at the end.
Right up here?
Right.
How do you factor that? Is that what you mean? You're going to factor this? Or are you just going to factor what's inside? The radical.
Inside the radical, I would assume.
What's that?
I say inside the radical, I would assume. I'm not
Okay,
sure.
but how do you then take a derivative of? Okay, inside the radical you have 1 plus x times 1 minus x. But it's still inside a radical. And I don't know how to integrate 1 over that either. So,
It just doesn't help.
say again?
So it just doesn't help anything.
Yeah, it doesn't help. I mean, you can do it, but I don't see it. It actually almost makes it seem more complicated. But a substitution is the only way I know to go there. There may be another way, but I just don't know it. Okay? Sorry. Okay. Now, did we get the answer? All right, that was example 3. How are we doing on time? Okay, let's do example 4. Okay. If I can find example 4, there it is. Okay. That is the integral. This is an indefinite integral here. X squared times the sine of x dx. Okay. Anyone think of any way you can do that straightforwardly? Take the, in other words, can anyone think of some function when you take a derivative, that's what you get? I can't. Okay. But it's a product. And let's see what happens if you take derivatives or antiderivatives. What would be your inclination?
U equal sine x.
Okay, then d will be cosine x, right? dx. But that makes your dv be x squared dx. So then when you do the antiderivative, that becomes an
Fraction x cubed over
3, which gets worse. The other doesn't get any worse, but that one does get worse. It's going up in powers. I'd rather it go down in powers. So I would say let,
x squared be
yes, let's do that. Let u equal x squared, then dv has to be what? That's not all.
dx.
dx, got it. Okay. Then, what do you do the next step?
du equals
du is equal to
2x
2x what?
dx
dx. And v
equals cosine.
is what?
Equal to cosine?
Not quite. Close, but not
Oh,
quite.
negative cosine?
Negative cosine x dx. I know why you wanted to do that to be the u, because you like the derivative of sine, you don't like the antiderivative. You always forget that sign, right? I know you're thinking now. I've had you too long. Anyway, okay. So that's a minus sign, because derivative of cosine is minus sign. So you'd have to have the minus cosine derivative of that to give you a positive sign. Okay. Now, what's the next step? Your original integral is now,
X squared times minus cosine.
yeah, uv, so that's a minus x squared cosine x, and since it don't have limits on it, that's all we put. I left them off before, sorry. This one doesn't have them. Then what? Okay, minus, okay, the integral of the bottom line, the way I write it anyway. And what would that be?
Minus 2x.
Okay, I'm going to do the 2 on the outside, and that minus is going to make that minus a plus, and that leaves me with a cosine x, no, x cosine x dx, right? Yay or nay?
Just gonna write it the other way for right now, so I get all the steps.
What's that?
I'm just gonna write it the other way right now, so
Yeah.
I get all the steps.
Okay. Okay, your x squared times minus, that's minus x squared cosine x. Okay, that's all right. Then you had a minus the integral of the bottom line, but that bottom line had a minus in it, so that makes the minus a plus. The 2 can go on the outside, and then what's on the inside is x cosine x dx. Oh, y'all let me get away with that, and that wasn't right. You don't put this dx there. The v doesn't have a dx with it. It's only the du, so shame on you. Okay. Okay? Got it? Now, can you do that integral? No, I can't. Okay. But what does it look like a method that might work?
Substitution.
Really? What would you substitute?
Nothing.
Guess what? Integration by parts again. Because it got a little simpler that time, didn't it? So let's do it again and see if it gets simpler again. So now we're just going to do that integral. Now I'm going to let that rest up there for a minute and bring it down here. I'm going to even leave off the 2. What we're investigating now is x cosine x dx. Okay? And what might you let be what? Help me.
The u would be cosine.
Let u equal, okay, there you go again. You love doing the derivatives of those and you don't like doing the antiderivative. Now let u be x. When you take derivative of that, it's going to get simpler, right? And dv. Now, if you like using different letters, go on and use different letters if this confuses you, but I'm keeping it contained here. dv would then be the cosine x dx. What's left? Then, what's next? du is equal to what? dx, perfect. And v is equal to what? Second? Is what? The antiderivative of cosine x is? No, sine x. Derivative of cosine x is negative sine x. The antiderivative of cosine x is positive sine x. Because derivative of sine is cosine. Okay, so that's just sine x. Alright, so this part we're going to take and write it as uv, which is x sine x minus the integral of your bottom line here, which is sine x dx. Okay, I think we can do that one. This is just x sine x minus, and what's the derivative of the antiderivative of sine x?
Negative cosine.
Perfect. So the minus is going to change that back to a plus cosine x. Okay, and then you can put your plus c there, or you can wait a minute and do it up here, and this will be minus x squared cosine x plus 2 times this answer we got here, 2x sine x plus 2 cosine x plus c, because that is an indefinite integral. Okay? I hope I got all my SIGN signs right. And let's see what we got. Minus x squared cosine x plus 2x sine x plus 2 cosine x plus c. Got it. Now here they do a little warning here. This is what Clark was trying to lead me astray in. If you do your first part using this as your u and that as your dv, if you go and reverse them on the next time, you just wind up where you started with, basically. So you get nowhere. You call that spinning your wheels, okay? It's not getting anything. So once you chose that, then the next time you've also got to choose the u to be the polynomial part and the dv to be the treatment. Okay? If you did it the first time and it seems to be doing all right, do it the same process. If you reverse them, then you get that back to an x squared, you get back to a sine, you're back where you started with, and you can have it solve your problem at all. Now, I have a feeling there's one coming up, but whether we're going to have time to do it or not, I think we will. There's some times that you have to integrate by parts a couple of times, and at somewhere down the road you wind up with the same integral you started with. Well, then if you do that, then add or subtract, or usually add it to the other side, and then half of what you had left over there is your answer, because you just treat the integral as a variable and go with it. I don't know if we're going to get to that before we run out of time or not. Let's see if we can do example 5 first. Okay? So I'm going to erase what I got here. Okay? And here's example 5. Find the integral of, and this is indefinite, secant cubed x dx. frankly, if this was up to me, I look it up in a table because I know that one's in a table, okay? But they're wanting us to do it by integration by parts. Okay. Now is head scratching time. I'm not doing a good job scratching my head. But I think I know a trick here. Let's try this first. Let's rewrite this as the integral of secant x times secant squared x dx. Now, what would be the advantage of that? Can anyone think of an advantage of doing that besides making it look more complicated? Second?
How is that an advantage?
How's what?
How is that an advantage?
Okay, that's the question, isn't it? Well, let's think. Are either of those a derivative of something else? That's the question. What's it a derivative of?
I can't read you.
Second? Yes, the derivative of tangent x is secant squared x, isn't it? Ha! Okay, we may have something here. So let's let u equal secant x and dv equal secant squared x dx, because we know what the v is going to be, don't we? All right. So then, what in the world what do we do next? What do we do next?
Take a derivative.
Du, and what would that be? You remember that one? If you don't, go back to your inside cover and do the derivative of secant x, and it's secant x tangent x dx. Secant x tangent x dx. This somehow doesn't seem like it's getting much simpler, does it? Until we get here, what is your v then? You just told me a little bit ago.
Tangent x.
Tangent x. Okay, good. Now let's see what this becomes. This will be your u times v, which is secant x tangent x minus the integral of the bottom line here, which is secant x tangent squared x dx. Are we any better off than where we began?
No.
Doesn't really look much like it, does it? Okay. Now, so I may have led us down a false path here. Let's see if I did. That's exactly what they've done so far in the book. Ha! Clever of them. When you see this tangent squared, they thought Pythagorean identity. I didn't think that. I should have. So I'm going to start over from here. That would be secant x tangent x minus the integral of secant x times, and what is tangent squared x? Pythagorean identity. Okay, they don't go that far. Pythagorean identity. Okay, what I do sometimes is this. I jot it down. I know that sine squared plus cosine squared, I'm leaving off the x's, is equal to 1. If you divide that by cosine squared, that would be tangent squared plus 1 is equal to secant squared, right? So tangent squared is secant squared minus 1, right? Okay, so that would be secant squared x minus 1 dx, right? Yeah, that's how I do it, yeah, because I don't memorize well. So I go back and it's pretty easy to do, okay? Now, again, this doesn't seem like it's gotten super much easier. Remember, all this is equal to that, okay? Remember that. We'll come back to it in a minute. Well, let's continue with this. This is minus the integral of secant cubed x minus secant x dx. Right?
Where did the cube come
I'm multiplying that secant x out front times the tangent squared, which is we got from my Pythagorean identity. So secant times secant squared is secant cubed, secant times secant.
from? Oh.
Yeah, I just distributed. Okay? Now here's what I was talking about just a little bit earlier. Okay? This is a real pain in the neck, but it's true. I mean, it certainly is there. Okay? I'm going to go back to the very beginning and start over. I mean, not start over. The integral of secant cubed x dx is equal to secant x tangent x minus the integral of secant cubed x plus the integral of secant, this has a dx in it, secant x, not dx, okay. I do that every now and then by Freudian slip, obviously, okay. Now, what you notice here, you can add this integral of secant cubed x dx to both sides. Okay, and lose it there. Okay, now this secant x, if you don't remember this, I'm going to write it. This is cosine x to the minus 1, right? It's 1 over cosine x, or cosine minus 1x, probably that would be. I don't know, that's no better, okay? In fact, it's worse. What I would do with the secant x there is look it up in the table, okay? Integral of secant x is log of absolute value secant u plus tangent u. That's what I do with it. You could go back. This won't work. That means I would have looked up the first thing in the table. I told you that at the very beginning. So anyway, what you have here is 2 times the integral of secant cubed x dx is equal to secant x tangent x, okay, that becomes tac sometimes, plus, and this is the log of absolute value secant x plus tangent x. I don't know if you remember that one, plus c, well, you don't have to do the plus c yet. Then divide everything by 2. So what's your answer? Integral of secant cubed x, that's what we're looking for, dx, is equal to 1/2 secant x, I did it again, secant x tangent x plus log of secant x plus tangent x plus c. Boy, what a pain in the neck. And that's what they get. 1/2 secant x tangent x plus 1/2, they distributed that in, log of secant x plus tangent x plus c. And sadly, we ran out of time. Sorry about that, folks. So let me explain what we do for the rest of it. Okay? Now everybody has your test 3, right? Everybody got it now. I gave the last one. Okay. So let me find, and it actually says on the top, test 4, doesn't it? I mean test 1. Your test 3 says test 1. It's not. It's test 3. Okay. Here is the last test. This will be your test 4, but it says test 2. I guess this is making sense. Okay. And it's going to take some explaining. Okay. So let me give it to you first. Now this is not your other test 2. This is the new test 2. Which rewrite that. Write it as a 4. You want to take one for what's his face? I don't have my copy anymore because I just gave it away. So let me, I think I still have it back here. There it is. Oops, no it isn't. Where is my original? Everybody check yours and make sure you don't have writing on the back of it. Wait, I think I found it. Yes, I did. Whew. Heart attack time. Okay. Is it start with finding the equation of no? Is that it?
Find the indefinite interval.
Okay. I may have left it down in the copy room. Yeah. Okay. What's your first one? Find an indefinite integral. Okay. Where in the world is my original? It may be back here. Make copies of that one at the same time.
This
Okay. Man. Okay, wait just a second. Okay, rather than waste your time any longer, let me borrow one of yours, but you'll have to remember what I say. Okay. Number 1, I think that's, just do it, okay? Number 2, yeah, pretty sure you can do that one. Number 3, I'll just tell you that's, if you look at that, don't you think that's an integration by parts? Number 4, set up for an integration by parts. Okay? Now, that's all we got to cover in class, 1 through 4. So basically, those are required for the final. Now, if you can do any of the rest of those, I wouldn't get spending way too much time on them, but if you can figure out a way to do any of the rest of those, if you get them right, they're bonus. If you get them wrong or leave them blank, they don't cost you.
how much?
So I'll have to determine that. What I do, I have a couple ways to figure it. I figure it both ways, and whatever gives you the best score. That's what I do.
I will spend hours if I have to.
Well, that's why you take your choice. And I would say you've got plenty of other things to work on, so I wouldn't spend hours on this. Just do the first 4. Unless you get everything else done and you have some time left, then you spend whatever hours you want to. But you got other tests you got to get, right?
Oh, yeah.
Yeah. So that's why I say do those first, then do those 4. If you have any time left over, try the others. Okay?
So when is all this due?
Okay, that's a good question. Are any of you graduating this term? You are. Unfortunately, yours is due by Tuesday morning, first thing. If you can get it to Monday, that's great. Very first thing Tuesday morning, because your grades are due in at noon on Tuesday, so I have to do it. Is Jordan also graduating this term?
No,
Okay, all right. So you're the only one graduating this term. The rest of you, before end of business on Thursday. Because you see, Friday, I'm over on the Birmingham campus. I may come in here Friday morning because I thought graduation was in the morning, but I think graduation is in the afternoon, isn't it?
Yes,
At 1. Okay, so I'll be here Friday morning. So if you get it to me early, first thing Friday morning, that will be okay too. But I'm going to have to leave here probably by 11:30. What time are y'all required to be at graduation? Do you know? 10? Ew, I hope we don't have to be there that early, but if we do, then I'll be over there before then. But I think if I leave here at 11:30, I'll be there by 12, and then whatever lining up they need to do for us, hopefully won't be as much as for y'all. I'll find out. I should know by now, but I don't.
I will find it.
What's that?
I said I'll find it.
Okay.
This is the time.
That is the final exam.
We can bring them back on your Wednesday next week.
What's that?
When do you want to do back?
Okay, that's what I was saying. If you're graduating, it's due back by the first thing Tuesday morning. You're not graduating the first thing Friday morning. Okay? So anytime sooner than that would be fine.
Okay, so you'll be here on campus on Monday or Wednesday?
What's that? I'm going to be on campus all next week until Friday around 11:30. Then I'll be on Birmingham campus. I'll leave to go to Birmingham campus. That's why I said if you get it to me first thing Friday morning, I can work on it here. Okay?
Are we meeting Monday?
No. Monday is finals week.
So you'll be in this classroom Monday? Or,
I'll be either in the classroom or my office Monday all day long. I have okay, let me back up. From 8:30 till 10:20, I'm doing a review session for one of my classes. Okay? And then after that, I'll either be up here if I'm giving an exam, or down in my office if I'm not giving an exam, or I may be in any classroom between here and there in my office. Tuesday morning at 8:30, I'm giving an exam down in room 205. That class is too big for this room, so I'm giving that exam down there. But after 10:20, 10:30, I'll either be back here or down in my office, or at some classroom in between. So, and after Tuesday morning, I'm either going to be 255, 265, or something in between for the rest of the week up until Friday morning. Okay? Good deal. And the other thing, I think I asked you earlier, have y'all done the student course evaluations? Yes, you have. Please do them. Please do them. Clark wants to wait till he sees his final grade. That's okay, you know. Or he may decide now that he's seen the final exam he wants to do it, you know. But yeah, he'll make a choice sometime. But don't go home without it. Don't go see. You can't get anything from Santa Claus until you do your course evaluation. That's what it turns out being. Okay. And I want you to get something good from Santa.